Hi, welcome back. In today's video, we're going to be having a look at prioritized planning, known as PP. This is essentially, I think, the simplest MAPF algorithm. It's extremely intuitive in order to understand why we might attempt this approach, and it is very, very surprisingly performative and very popular in practice, just due to how simple the idea is and how it actually works quite well in practice in real large grids with lots of agents. So let's dive into immediately then, what even is prioritized planning? Well, really, it is just the very intuitive idea that we have a bunch of agents, we need to plan their paths, we need them to be collision free. Well, it's just the hand wave approach. Okay, I'm going to treat each of these as an individual search problem, essentially, where we have moving obstacles, right? Dynamic obstacles. These moving obstacles will be other agents. Now, of course, we need to plan these in some sort of order. The idea is as simple as we're just going to search for one agent first, ignore all other agents, then we're going to plan for the next agent, and he has to avoid agent 1, right, to avoid collisions. Then agent 3 will go and have to avoid all agents before him, and so forth and so forth and so forth, right? We are simply creating some form of ordering, which we're going to call a priority ordering, which means agents with higher priority get to go before all agents with lower priority. What that means is that the agent with the highest priority has no other agents, no other obstacles besides those that would already exist in the map itself. And essentially every agent thereafter, right, has increasingly more agents to avoid. And we're just planning safe paths according to, of course, dodging those moving obstacles. Prioritized planning is extremely simple. This is its main pro, right? Extremely simple to understand and to implement. And as well, because we're doing a very, very, very simple thing, we're just essentially doing single agent search, right, with moving obstacles. Compared to the other advanced centralized controllers or advanced approaches we'll see to avoid collisions in these other MAPF algorithms we'll look at in the future, this is an extremely fast method because it's very simple and computationally feasible. Just plan single agent paths. We've been doing this for ages. We've just had a look at both TXA star and SIP as well as these really, really fast solvers for temporal problems. Cool. Now, the downside of prioritized planning, though, as I'll say in spoilers, before we go over and show all of these kind of situations in the worked examples over here, is essentially that it is definitely not an optimal algorithm, okay? So even when optimal solutions exist, prioritized planning cannot find them. It does not guarantee to find them. It absolutely can return an optimal path, but again, we define optimality in our algorithms in terms of this guarantees. So prioritized planning is a really nice, simple, fast approach, but it does not provide us with the guarantees that we would like in this area. And then as well, it is not complete in general. So there are essentially certain problem setups that we can use that actually do technically guarantee that it will be complete. But oftentimes, right, your problem, you don't have too much control perhaps over those initial variables and how you define the start and target locations from the get-go. And in these cases, well, prioritized planning is not only not optimal, but it also is not guaranteed to be complete. Even if a solution does exist, prioritized planning it may not find it at all. Now, the last thing I want to note as well really is just that inherent in all of this, we had to rank the agents, right? And we're going to be talking about some of that over here. Well, we essentially, it is not clear how to order priorities. Okay, so choosing a correct or an optimal priority ordering is extremely difficult in its own right. There are a bunch of algorithms that will kind of build upon these ideas, one of them being PBS, priority-based search, where we're actually searching over this meta high level where you're actually searching over different orderings to try to find the best ordering. But essentially, this is a con in this situation because this is actually not a trivial problem in its own right. Coming up with the optimal ordering is in itself another extremely difficult problem. It will also be an NP-complete problem, actually. So then let's dive over here to essentially explore some of these scenarios I've posited here. So these are, I'm just simplifying kind of like a grid map into this node-based thing. So the blue nodes are locations we can be. We have two agents, a red agent A and a yellow agent B. Their goals are on opposite ends, so of course they're going to have to interact to come together. So let's explore essentially, imagine if I gave priority to agent A. Okay, I say you get to go first. Well, what we're going to see is, of course, agent A is going to smash its way across directly to the goal. Okay? So take a second to think what this means for agent B, because agent B gets to plan next, of course. In this situation, it will attempt to continue across to the right on its own. So it will do this. However, it gets to this node here, and both agents at the same time steps are attempting to occupy the same space. So because agent A planned first, it had the higher priority, well, B sees this position as blocked, okay? So what it really does is it goes to here, attempts to look, wants to go this way, realizes it can't. Then it will wait at this location, right? So it waits at this location once, but then in the next time step, it sees that this location now is reserved. Remember, it can't simply swap with the other agents because we have in MAPF problems the idea of not only vertex collisions, you can't occupy the same place, the same vertex at the same time. There are edge collisions. You can't have two trains go through each other. They will, of course, collide. So what that means is B gets kicked out. He has to go back to his home base. He waits there. Now you get an actual infeasible collision. There's no remedying the situation. Agent B has nowhere else to go. It can't get out of the way. We have the standstill issue, right, where neither of them can get out of the way. Now, I will draw up an interesting example as well. So if I modified this and added a second node over here, well, in this case, it's great, right? Okay, fine. Agent B would be able to get out of the way. But what happens next? Well, agent A is going to arrive at its goal and stay there, okay? So depending on the type of problem you define, agents sometimes can arrive at their goals and then just vanish, and then agent B would be okay. But most of the time, we're usually considered, of course, it's like a train. It arrives at its station, it's going to park itself there, and it is completely blocking the path. So all of this is to say, in this top example here, this is infeasible. There is no solution that is found. So no solution found. What is interesting is, of course, as a human being, we note that in a cooperative sense, there would be a solution. There's this central node here, right? So if one of the agents ever went up to wait here, well, of course, the other train, the other agent would be able to pass, and then they would both arrive at their locations. So in this global viewpoint, we as human beings, compromising human beings, see that there is a valid solution to this problem. Prioritized planning cannot find this because in its nature, in its essence, it is a greedy solver. Each agent acts completely greedily in its own best interests with no regard for the other agents. So essentially this happens because agent A is going to, with a higher priority, forge its way directly across without ever knowing that agent B was going to have to come this way as well. So ta-da, this had a valid solution as a human being. Prioritized planning could not find it at all, right? Not complete in general. Let's have a look at a very similar problem now, but I've moved the little out of the way solutions. So here is a problem where, again, let's say that the priority again will just go to agent A, and agent A is going to beeline away directly across. Now, the same situation happens where agent B will get to this location. It tries to go here, realizes it's blocked. Now, what it will do is wait, again, one location here, because it likes this location. But it does see again that it's about to be blocked and it needs to do something. So what does agent B do? Well, it will explore both avenues, right? In the search space, it will also check that it could go back, see if that works. But it will see that the version that leads to a solution will be that it actually goes up and avoids the thing here. So it will go up to out of the way, and then it will wait one time step, it will go down and continue on its way. So here is essentially the same problem as we just saw above, but we have a different solution. So here, it actually finds the optimal solution. So that's interesting, right? So I just want to point out that in this situation, this is the optimal solution. It was able to find it. This is definitely not guaranteed, okay? So let's show that final bit. So obviously it can still find the optimal solution. How about this version here? So before I get into it, let's just reason as human beings what the best solution would be to this bottom problem here. Essentially, the spoiler alert is that weighting in the center is going to be the best version of this path because it involves less weighting, okay? So let's dive into, though, what the agents are doing in this situation. Again, prioritized planning, nice and simple. Agent A goes to its target, doesn't care, has really good priority. Agent B in this situation does the same thing as we've been observing. It tries to go all the way across, gets to this location here. This is blocked. So what it will do is it will wait, it will backstep, it will go up, it will wait, it will go down, and continue on its way all the way to the goal, okay? So I don't remember the exact numbers, but if you track up this score, there's a whole lot of wasted time if you think about it, because we essentially have the whole period of time here where we're waiting. Well, essentially the yellow agent was taking a long time to progress through this area, so we ended up waiting more time. I'll show you that the correct version of the solution in a cooperative environment would actually be that the pink agent or one of the agents needs to go up and be nice and wait in this center location. In this situation, the optimal solution would be found. And so essentially, okay, what's happening here? So this was a tick after all, I guess. Now this is like okay, like we found a solution. So a solution was found, but not optimal. Okay? So here's the third case. We actually were able to find a solution. Prioritized planning gave us something. It was okay, it's better than nothing. But there was this mythical third option. There was the optimal solution, and we completely missed it. So this is prioritized planning. I think it's extremely easy to understand and to implement, right? And I think what's really not apparent in a lot of this discussion is in these very small, congested, single hallway examples, right? Things can look difficult. But in real problems where you have these large open areas or just hundreds of agents moving around, prioritized planning honestly does pretty well. Oftentimes, of course, based on one priority ordering, you may not be able to find a solution. But because it's so fast, well, what you can do is maybe just try a few different priority orderings. You can explore things like PBS to actually search additionally on different types of priority orderings. Or maybe this is just like a first go-to solver, try to find a solution quickly, and then use another algorithm to improve it thereafter. There's a million different things, and please stay with me as we take you, though, beyond prioritized planning into real MAPF algorithms. We're going to first start with the idea of centralized A star. That stems from this. We're seeing that prioritized planning is greedy and is unable to find these happy medium solutions because of the idea that each agent was acting independently and individually, right? We know that as human beings, if we were a central controller, right? If we had a bird's eye view of the whole problem, we know that we can make decisions for the good of the many that are essentially violating each agent's greedy independence worldview, and we can find better solutions that way through a bird's eye centralized controller. Well, that is where centralized A star comes in. Please join me in that video, and thank you for watching.